This second video is going to pick up with example 4. As you can see here, normally this would start with a handout. I know this might not look completely great, but you can see this is the handout. This is on Schoology in with the notes for class, so this was a separate file for the worksheet. So you can either copy down the work that I'm going to do on this, or you can just follow along with this. These are in the textbook as well. So your situation here, you have a dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second. It says it reaches a height of s equals 160 t minus 16 t squared feet after t seconds. So first question for part A is, how high did the rock go? So here's my S equation. I see we're still a little bit off in that one area. Let's try this just one more time. I feel like I've had to do this an extra amount today. Okay, so we have S equals 160t minus 16t squared. That is my position, and we want to know how high did the rock go. So there are a couple different ways you can think about this. You could look at this from an algebra standpoint. This is a negative quadratic, so it is something that's going to go up in the air and it's going to come back down again. I can see we're really loving that today. So the peak, how high it actually goes, that is going to be the y value of your vertex. So if you remember how to find the vertex of a quadratic, you could take that approach. You could do your negative b over 2a, and then you'll plug back in and figure out what the y value actually is. Or you could take the calculus approach, because when that rock goes up and hits that peak, it is actually going to stop moving. And when it stops moving, its velocity is going to equal 0. So if we calculate the velocity here, that's going to be a ds dt. So that's going to be 160 minus 32t. And I want to set that equal to 0. Because where the velocity is equal to 0 is where the rock is going to stop moving. I will have to then plug it back into the original to actually figure out the height. So if I solve this equation, I'm going to add the 32 to both sides. So I have 160 equals 32t. Divide both sides by 32, and t is equal to 5. So t is a time. This is actually 5 seconds. So it takes this rock 5 seconds to reach its highest point. But to actually find how high it goes, I have to find s of 5. So that's going to be 160 times 5 minus 16 times 5 squared. And if you do the math on that, I don't know why we are really messing up here today. Let's see here. That is 400 feet. So 400 feet is going to be how high the rock goes. So now we're at part B. What is the velocity and speed of the rock when it is 256 feet above the ground on the way up and on the way down? So I want to know what my velocity and speed are going to be when my s is 256. So we are actually going to plug that in. And this one is actually going to be more of an algebra question than a calculus question, because we are solving this equation. 256 equals 160t minus 16t squared. I need to get everything on one side, so I'm going to move everything over to the left. So I have 16t squared minus 160t plus 256 is equal to 0. We can actually divide all of these by 16. And then this is quite easy to factor. So we get an 8 and 2 seconds. My height is going to be 256. Of course, it's going to be 2 on the way up and 8 on the way down, because again, it reaches its max at 5. So it doesn't make sense that these are the same distance away from the center. And now to find the velocity, we would actually plug these times into the velocity equation. So if you remember, we had this velocity equation over here. That one we are going to plug into there. So v of 2 is 162 minus 30 times 2. And I'll look in 2 there. But with that, you end up with 96 feet per second. V of 8, 160 minus 32 times 8. That's going to be negative 96 feet per second. So at 2 seconds, it's going to be 96. At 8 seconds, it's going to be negative 96. Your speed is just going to be the 96 seconds. Or I'm sorry, the 96 feet per second. So again, your speed is your absolute value of velocity. Now we have part C. Part C says, what is the acceleration of the rock at any time t during its flight? So acceleration is going to be the derivative of velocity. So if you recall, our velocity equation was 160 minus, I do not know why this is so terrible. Let's try that one more time. Velocity is equal to 160 minus 16t squared. So the derivative of velocity, wow, this is really, really bad, is acceleration, and that is going to be negative 32t, and it says, I'm sorry, there should be no t there. This board is throwing me off with how terrible it's acting this afternoon. This is just going to be, let's try this again. Messing up my velocity equation here. So my acceleration is going to be negative 32, and that's feet per second squared. There is nothing to plug in there because your acceleration is constant. So at any time during the launch, the acceleration is going to be negative 32 feet per second squared, which makes sense because that actually goes with what we had on the previous page for the acceleration due to gravity. Now you have part D, when does the rock hit the ground? Well, the rock is going to hit the ground when the position is equal to 0. So we're going to let the position function equal to 0. When we factor that, I can actually factor out a 16t, and then I'm left with 10 minus t, which gives us 2 different times. You get t equals 0 and t equals 10. Well, 0 seconds is where it starts. So it doesn't make sense that it would hit the ground after 0 seconds. That's where it starts on the ground. So 10 seconds is actually going to be your correct answer there. So that one was pretty involved. You did have to use some calculus and some algebra there together to figure some of those things out. Okay. And now we have example 5. This one is pretty long. There's quite a few parts to that. If my notes are correct, this actually goes up to, I think, part E. So there's quite a bit going on here. I may not write everything down. It all depends on how my board is acting whenever I'm going through this. Okay, so we have particles moving along the line so that its position at any time t is greater than or equal to 0. Notice we're not dealing with any times that are less than 0. Is given by the function s of t is equal to t squared minus 4t plus 3, where s is measured in meters and t is in seconds. So first thing they're asking us, find the displacement over the first 2 seconds. Well, displacement, if you recall, is the position when you end minus the position when you start. So it's going to be s of 2 minus s of 0. Well, s of 2, 2 squared is 4, 4 times 2 is 8, 4 minus 8 is negative 4, plus 3 is negative 1. You start at s of 0, which is 3. 0 squared minus 4 times 0 plus 3 is going to be 3. So your displacement is going to be negative 4, and it says, measured in meters, so it'd be negative 4 meters. So there's a 4 meter difference from where I begin to where I end. The average velocity during the first 4 seconds. Average velocity, you see the word average there, that's going to be a slope. So this is going to be s of 4 minus s of 0 all over 4 minus 0. Now notice we're finding s of 4, not s of 2, so you can't just reuse your answer from part A here. So I do have to plug in 4. S of 4, 4 squared minus 4 times 4, that's 0, plus 3 is 3. And then, of course, s of 0 is 3. So your answer is going to be 0 meters per second. The average velocity here is nothing. Because it's going to be stopping and starting in the same place. So it's almost looking like it didn't move anywhere, although we know for a fact if at 2 it's at a position of negative 1, it was in fact moving. But the average tells us that it's 0. Part C, find the instantaneous velocity of the particle when t is equal to 4. I'm going to recopy that equation so that we have it. Maybe I'll be recopying it. S of t is equal to t squared minus 4t plus 3. To find the instantaneous velocity, that is the derivative. So I have to find ds dt, which is the same thing as my velocity. So that's going to be 2t minus 4. And we want to know this answer at 4. So we're really comparing the average velocity with the instant velocity. So I'm letting t equal 4. That's going to be 8 minus 4, which is 4 meters per second. So you can see there that the average and the instant, they're actually quite different. Because if we went by the average, we would say that we weren't moving at all, whereas the instant velocity there is actually 4. Now the acceleration, remember acceleration is the derivative of velocity, which is the second derivative of position. So this is dv dt, which is the same thing as d squared s over dt squared, which is acceleration. And that is going to equal 2. If we take the derivative of 2t minus 4, you just get 2, and that's meters per second squared. So it actually doesn't matter where we're at. I know this says at t equals 4, but there's nowhere to plug in the 4, so your acceleration is just going to be 2. Part E, this one is pretty involved. It says describe the motion of the particle. At what values of t does the particle change direction? So we know that we are beginning at 3. So at time equals 0, I am at 3. At time equals 2, get over there eventually. At time equals 2, I'm at negative 1, and I am also back here at time equals 4. Boy, this is just not liking us today. It's amazing how a couple of hours can make a difference here. So we need to be sure that we have checked to see all the places where we are changing direction. You are going to change direction where your velocity is equal to 0. So I'm going to go back to this velocity equation here. Okay. I'm going to set that equal to 0. And when I do, you can see we get 2 for that answer. So 2 is where we are changing direction. And you can also look at the signs, because if I have a value in between 0 and 2, this velocity is actually going to be negative. So like if I plugged in 1 or a half or any of those things, I would get a negative velocity, which means I'm moving to the left. So I'm going to start off moving to the left until I get to 2. Once I get to 2, then if I plug any number that's bigger than 2 in here, I'm going to get a positive velocity, which means I'm going to be rounding the corner and then moving to the right, and that's where I'm going to keep going. Your book does have a really good explanation of this. I don't want to do too much with that. And again, you can see part F, use the parametric graphing to view the motion of the particle on the horizontal line, y equals 2. I'm going to pull that up real quick just so you can see that. Maybe I'm not going to pull that up. Let's try that again. Again, you can go by what your book has with this. This may be a struggle for me to actually graph. So I will see what we can do here. If this is not working out correctly, this may be something that I have to come back to later on. Actually, change our mode to parametric. Either rather than struggling through this, I think I'm going to come back to this whenever I'm sitting at the computer and I have more control over what's going on. So we're just I'm going to leave that for right now. Hope that I can get rid of that. So we will come back to that. I'll do another little addendum with that one. Okay, so the last thing I want to talk about is sensitivity to change. And this is, you can see here, when a small change in x produces a large change in the value of the function, we would say that the function is relatively sensitive. So, for example, if you plug in 1 into a function and you plug in like 1.2 and you get hugely different values, that would be a function that is very sensitive to change. Your derivative can be a measure of that sensitivity. And there is an example in your book that goes over this. So this, again, is not something that we are going to be going over together. This is something that I want you to read about in your textbook. There is a whole other part to this, and you may see this in the video for the book that deals with economics. We are not going to be going over the economics part in this class just because of time. But if you are thinking of going into business, it might be a good idea to listen to that part of the video and to read over how that is used as far as calculus goes. So that's going to wrap up our notes for 3.4. This is your homework assignment. It is due Thursday. I think I do have a deadline of midnight, but plan on Thursday we will be starting our lesson for 3.5. So really don't plan on doing all of the assignment on Thursday. That probably wouldn't be the best idea. Go back through, watch this video, watch the other video, watch the video from the book. Let me know if you guys have any questions at all.